All right, now we study a very useful tool called the moment generating function for calculating various moments, as the name suggests. So, first the definition. The moment generating function of a random variable x is defined as the expectation value of the exponential of tx. Okay, here this t is let's say it's a parameter and it's a variable of this function m of t, and we multiply it with x and take the exponential of this, and that's moment generating function. So why is it useful? Okay, remember the Taylor series of Taylor expansion of exponential function? So formally, this exponential function can be expanded as this: x t square x squared 2 factorial t cubed and x cubed and 3 factorial, and so on, right? So in general it's like this: 0 to infinity tn xn n factorial. Okay, so take the expectation value of both sides here and here. Okay, so this is the moment generating function, right? And on the right hand side we have this constant 1. So expectation value of a constant is that constant. And this one here, t is not a random variable, so it can go out of the expectation. So expectation of x, and same here also, t squared divided by 2 factorial and expectation of x squared, and t cubed and 3 factorial expectation of x cubed, and so on. So now let's put t equal to 0. What happens? So this is m of t. So m of 0, so t is 0. So all terms that contain t will be gone. So this is 1. Okay. Now, that's not very interesting. Let's differentiate the moment generating function with respect to t. Okay. So dm dt. Okay. So this one will be gone and this t will be gone, and we have expectation of x, and this is differentiated, and we have it's 1, and differentiated we have 2 and expectation of x to the power of 3, and so on. Then again put t equal to 0. So let's say let's put this m prime. Okay, m prime of 0. So all terms that contain t here, like this one, and so on. So essentially all the terms except for the first term will be 0. So what we are left with is expectation value of x. So you differentiate the moment generating function once and put t equal to 0, and you get the expectation value of x. Nice. And now we differentiate twice, once more. Okay, so second derivative of m of t. Now you differentiate this with respect to t, and this t will be gone, and this is a constant now, and it's gone. So we have expectation value of x squared, and we have t expectation value of x cubed, and so on. Now again, set t equal to 0, then all the terms will be gone except for the first term. In this case, the first term is the second moment, about 0. So in general, if you differentiate moment generating function n times and put t equal to 0, and yeah, put it equal to 0, you will have the nth moment. So that's why this function m of t is called moment generating function. It generates moments. Okay. Now let's explain the laws of large numbers. Do you remember when we calculated the sample average of some data? So here what we wanted to do was actually to estimate the expectation value of these random variables. Now, let's say we have n random variables, and all these are random variables. Okay, and suppose they all have the same mean, same expectation value. So x1, expectation of x2, and they are all equal to some finite value mu. Okay, and we defined the sample mean random variable as sum of these random variables. Okay, and of course this is a random variable. And what's the expectation value of this? And since the definition is this, and the operation of expectation value is linear, so we can just expand this summation. So sum of summation is summation of the expectation of summation is sum of expectation. So we have this, and all of these are equal to some constant mu, so we have mu. So we know this expectation value of the sample mean is mu, which is same as the expectation value of all these random variables. But every time we take a sample, let's say from random sample from omega, say omega 1, omega 2, these values are different. They deviate from the expectation value. So, if we only have one set of experiment, this may deviate from this expectation by a large amount, or maybe very close to this value. Who knows? So how can we estimate this error? And is there any way to reduce this deviation? Otherwise, these experiments are not so reliable. We don't know what to believe. And this question can be, in a sense, answered by the law of large numbers. And actually, there are multiple laws. Uh, Here we mostly explain the weak law of large numbers. So here's the problem setting. As I've said, we have many random variables, and each of them has the same mean. Okay, and also we require that the variance of these random variables is bounded. So there is some finite constant. That means less than infinity. So that means this k is finite. So the variance of each of these random variables are finite. Okay, so variance is finite. Under this condition, let's define a new random variable Sn, which is just the summation of these random variables. Okay, n of these random variables. Then this theorem says expectation value of Sn over n minus mu squared is 0. Okay, so this is called a weak law of large numbers. Okay, so what does this mean? Now this looks like variance, right? Actually, yeah, in a sense it's a variance. It's a squared deviation from some value. And actually this is the expectation of this quantity, Sn over n. Okay, so it is a variance, kind of. So this theorem says the variance of the sample mean will converge to 0 as the number of samples increase. Okay, so that's a nice result, because if we increase the number of observations, well, then we will have less and less deviation from the true expected value. Okay, by the way, uh, in this case we take some deviation and take the square, and that converges to 0, and we say okay, let's make this in circle. So if something, let's say circle squared, converges to 0, then we say uh, this sorry, I think maybe we should be more specific. So in this case we say Sn over n converges to mu in L2. So L2 here is kind of mysterious keywords, but it just means we square something. Okay, so if we square the deviation and take the expectation and take the limit, and that converges to 0, that means this quantity converges to some constant, in some sense. So in some sense, in this case means in L, in L2. Okay. Why L? I cannot explain at this point, but maybe in the future you will learn in some more advanced probability or real analysis. Anyway, and also it should be pointed out that when something converges in L2, then we can say it also converges in probability. So converges in probability. Okay, in probability. So that means this: limit n goes to infinity, probability of this Sn over n minus mu absolute value greater than any positive number, that will be 0. Okay, so this epsilon is any positive real number, any positive real number. Okay, so in general we can say if something converges in L2, it also converges in probability. Okay, there are many types of convergence. Convergence in probability means the deviation, this deviation is greater than any small amount, is 0 in this limit. Okay, so this deviation is, so this epsilon can be any positive real number, so that means this can be very 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 small, tiny real number, positive number. So that means this deviation can be very small. Any amount of deviation, that probability will be 0. So effectively, this ratio Sn over n, which is the sample mean, converges to this expectation value mu. Okay. Anyway, let's prove this weak